welcome to our Interact webinar, a brand new one. This time we'll talk about some science as usual, and as usual, this will be related to some polar topics, Arctic and Antarctic, some phenomena that can be encountered in those regions specifically. And I would like this webinar to have a little bit different form. So this will be some riddles that we'll start with, and you will have an opportunity to give it a little thought, and then we'll try to answer, not only find the solutions, but most importantly, find out why. But let's first start with a very basic question, which is not only polar science or geophysics related. Can we really explain everything? Can every riddle, every science riddle, or every riddle and every question be solved with science? Or do we already have all the answers to all the questions that that might come to our head, to all the phenomena that we observe? So this is a question like the intersection of science, of philosophy, of religion maybe, and could be probably discussed for hours. Today we'll of course focus exclusively on science, leaving the metaphysical questions aside. And also we will not talk about the crime riddles or other true crime riddles that I have another seminar dedicated to, which is I think quite interesting, but not very scientific. It's dedicated to some crimes that took place in polar regions, and some of them are quite mysterious or haven't been solved for decades. So this time we'll focus on science, and back in the very beginning of 20th century, a British physicist, Lord Kelvin, claimed that there is nothing new to be discovered. He referred to physics, but there was a conviction that there is absolutely nothing to be discovered more in science in general. And as you can see, it's the very beginning of 20th century. So it turned out to be quite different. In 20th century, only these are just the most important and discoveries only related to physics. So 8 years after this claim, Albert Einstein, the famous Albert Einstein, announced and published 4 papers on the theory of relativity. So with the publication of his theory of relativity and other works too, he changed our entire view of the world. So only 5 years later, we thought we knew everything, but it turned out to be basically the opposite. So the year this year when Albert Einstein published his theory will certainly remain most significant year in the development of modern physics so far, of course, because there's still more to discover. So we have Albert Einstein, we have Niels Bohr, who explained further with quantum mechanics some phenomena that couldn't be explained otherwise. We have Edwin Hubble, who observed distant galaxies, and he discovered that they are moving away faster than closer galaxies. So this meant that our universe is expanding still. So this was another huge discovery. So today we're going to ask ourselves 5 questions. I think that the puzzles may be some of them very easy for you, some quite surprising. But like I said, we'll be more interested in the mechanism of certain phenomena, and the answer yes or no is not enough. The most important answer is why. So the questions would be, which freezes faster, cold water or hot water? Is it easier to overhear someone in the Arctic than in other regions? Can you hear the aurora borealis? Because we certainly can see aurora borealis, but can it be also heard? It's the light, northern light, so can light be heard? And does Antarctica or the Antarctic maybe refuse climate warming, and is it as cold there as in the Arctic? And the last one, more human activity related, but not only, is it actually warm in an igloo? And of course, why? So let's start with the first one. Which freezes faster, cold water or hot water? The first riddle may be more freezing one than polar one, but quite interesting because the answer seems unintuitive, because we would think, okay, if we put hot or warm water, hot maybe, water out in the outdoors when it's freezing, well, maybe it's at first it needs to become cooler and then it freezes, so maybe it won't freeze so fast. But actually, it's quite the opposite, and frankly, it's not 100% explained, meaning that there are different theories about it, but it is definitely observed, and as you can see on this photo. It's so-called Mpemba effect. So this is a phenomenon which is named, as it often is, after its discoverer, that was Erasto Mpemba, and he actually lived not in polar regions. He lived in Africa. He went to school as a teenager in Tanzania, and it was in 1960s. But it's not that he was the first person who ever observed this phenomenon. It was already mentioned, for example, by Aristotle in ancient Greece, like many other phenomena that we later explained with more advanced knowledge of physics, etc. So what happened to Erasto Mpemba is that he went to school and he had a cooking lesson. And he was actually learning how to make ice cream by heating milk, sugar together on the cooker and letting the mixture cool before putting it in the freezer. So the mixture would solidify, quite simple. But Mpemba noticed something strange. When he put the hot mixture straight into the freezer, it was ready faster than if it had been left too cool. And why is that? Of course, it's not something that is advised, because it's for other reasons related to electricity consumption and the device, the freezer itself. But how is it possible that something hot, not something hot, a hot fluid freezes faster than cold fluid? So until quite recently, and by quite recently, I mean 2013, this phenomenon was like a paradox that was not explained at all. I mean, there were some hypotheses. For example, that if we boil the water first, it reduces the content of gases that are dissolved in it. Then there was a theory about evaporation. So the evaporation of water is done endo-energetic process. That means it doesn't produce energy, it consumes energy, and as such it accelerates the cooling of the water that is remaining in the container, in the reservoir, or whatever. Also, that evaporation reduces the volume of the fluid of water, and then it reduces its heat capacity. There was also some assumption that mineral salts dissolved in the water, such as calcium, magnesium, carbonates, which especially in so-called hard water, they lower its freezing point. That is a fact. And then the freezing point being the temperature at which the water solidifies. So in the process of heating, some of those mineral salts are precipitated, and so on and so on. But this actually changed, like I said, quite recently with a paper published in 2013. So it's a serious scientific paper. It's not some crazy theory by a couple of scientists from Singapore University of Technology. So they claim and they argue that this whole process is due to the unique properties of water molecules. What are those unique properties of water molecules? We all know that water is hydrogen and oxygen, and but the bonds between hydrogen and oxygen molecules are clear to us. This is what holds the molecule together. But there are also other there's also other type of bonds in water, and actually those bonds hold water together, and these are so-called hydrogen bonds. So which make water even more exquisite as a substance than we may have thought before. So they demonstrated experimentally that hydrogen bonds between molecules are different to those. They are called covalent bonds, those solid bonds between hydrogen and oxygen molecules. And they are different than those between atoms in a not between molecules, sorry, between atoms in a molecule. So hydrogen bonds are between molecules. And why are they important? Yes, they're absolutely important. For them, for example, there would be no way for the plants to take up water through their roots. So there wouldn't be any developed plant life on our planet without those bonds. So because water wouldn't go up the roots to other parts of the plant. So the phenomenon can be explained by looking at the molecular structure of water. Like I said, single molecule is large oxygen atom and two smaller hydrogen, and they are attached normally by covalent bonds. However, if we have more water molecules, they start to kind of cluster together with the help of those hydrogen bonds. And what does it have to do with our Pemba effect? So as water heats up, the hydrogen bonds, those between molecules, become longer, they lengthen. So the water molecules are further apart. And the covalent bonds give up energy, sort of, accelerating the cooling of the water. Let me rephrase this. Under normal conditions, these bonds, these hydrogen bonds, lead to the water molecules squeezing closer together. And these are normal conditions, but when heating up the liquid, so when it's hot, they loosen up, right? They're as you can see here on the on this image, there are short covalent bonds and long hydrogen bonds that allow to give up more energy, so it's accelerating the cooling of the water. I would say it's quite counterintuitive, but makes sense. At least since 2013, no one offered a better explanation, or no one really undermined what those scientists from Singapore University of Technology claimed and also proved experimentally. So the second question, let me remind you, why is it easier, or is it easier to overhear someone in the Arctic? Actually, why is it easier already indicates that it is indeed easier to overhear someone in the Arctic. And overhearing means actually, in this case, that we can hear voices, we can hear sounds better, more clearly, and from further distance. This is why if we wanted to overhear someone from the distance, it would be easier in the Arctic than that, for example, in Europe. And it's not only because we might think that there are empty spaces and not a lot of people around, so it's quite quiet in the Arctic. No, it's not. At least it's not the only reason. Actually, there is a more scientific reason. So, actually, in the Arctic, people can sometimes see and hear things they cannot see or hear in most other places in Earth, and this is caused by special atmospheric conditions. As for seeing things that cannot be seen elsewhere, I have another webinar about so-called polar illusions. So it explains several phenomena that can be observed due to specific atmospheric conditions that are, well, that are illusions that are not real, but on the other hand, they are quite real. They are just making our mind make our own interpretation of some of the images that are actually produced by those conditions. So some of the atmospheric conditions are microscopic ice crystals suspended in the air, changing the way light, but also sound travel over long distances. So now let's focus on those hearing, not illusions, but hearing experiences, let's say. So we have layers of warm and cold air that refract or bend light, but not only light, but sound as well. This is one thing. So we have microscopic ice crystals. They are suspended in the air. They are reflecting waves, because sound is wave, of course. And people sometimes in the Arctic, people report hearing noises from much farther away. And like I said, just like with the optical phenomena, this occurs because of cold atmospheric conditions. So the air near the surface tends to be cooler, colder, and therefore denser than the air above, which means that the sound waves tend to bounce downwards towards the surface rather than upwards from the earth. So in case of more temperate latitudes, for example, in Europe, in our latitudes, they tend to go upwards rather than downwards. So this is our beloved phenomenon of temperature inversion. So the range over which sound can be heard depends on the air temperature, but also wind speed, direction, rate of absorption of sound energy by the surface, and so on and so forth. Also, soft snow absorbs sound energy very efficiently. So it's muting sound transmission. So it's not very likely to overhear someone when we have lots of fresh snow around. But once we have a hard ice snow surface, it absorbs very little energy. So the smooth ice is like almost a perfect mirror, not only for light, but also for sound, because both are waves, obviously. So under the right conditions, conversations between people can be heard in the Arctic from as far away as 3 kilometers, of course, with no surrounding circumstances, additional noises. So if we want to overhear someone from a distance, it would be best to do it on ice, or on hard ice or hard snow. So basically, it sounds like Arctic or maybe more Antarctic ice. but actually in the Antarctic there is probably not much to overhear other than scientists on research stations. So we hear that the sound wave propagates further, a little bit slower, but further than in more moderate areas of Earth. And this bending and reflection from the inversion layer increases so-called amplitude of the sound wave. So the sound travels slower, but further. And again, about speaking of hearing or overhearing, the third riddle would be, can you actually hear the aurora borealis? We have some great webinars dedicated to the phenomenon of aurora borealis or aurora australis in the southern hemisphere, obviously. So it is certainly possible to see it, sometimes with very active sun, even in our latitudes, meaning in Europe, it is not unlikely to see to observe aurora borealis to some extent. But can we also hear it? So, and the answer is actually quite complicated. So, cut a long story short, about the aurora borealis, it's a phenomenon of light emission caused by the collision of high energy charged particles originating from the plasma emitted by the sun, solar wind, with our atmosphere, our atmospheric gas molecules, actually more precisely in the thermosphere. And we know that different gases emit different waves, waves at different frequencies. So this is why we see different colors during this auroral activity. Just to make it very, very short. Why do we observe auroras most frequently in these northern, far north or far south regions? So when charged particles enter the Earth's magnetosphere, they follow the lines that you can see here on this image. They follow the lines of the Earth's magnetic field into areas called aurora ovals. So, and those aurora ovals are concentrated around the northern and southern geomagnetic fields. Okay, so that was a very shortcut to the phenomenon of aurora borealis, or australis. But let's get back to the sound. Why is this slide titled "The Truth of Folk Wisdom"? Because people observed, or more like heard or reported hearing aurora for decades. At first it was regarded as folklore, some sort of invention, because also aurora was once very much feared. It was seen as a ghost of ancestors, evil omen, or something like that. So people thought, okay, scientists mostly thought maybe people feared aurora so much that they also imagined some creepy sounds made by aurora, because they reported quite creepy sounds actually. But finally, in 2012, a Finnish scientist, Professor Unto Laine-Zorza, he simply confirmed that we do have sounds audible to the human ear without question. He recorded it, and I think some of those recordings can be even found maybe on YouTube still if searched thoroughly. So previously, serious physicists claimed that no way, those were simply some auditory hallucinations because of the impression that aurora borealis made on people. But actually, now Hidiri did record this, so it is true. So okay, but why? How is it possible? First, they try to explain it by, for example, by pine cones. So the Arctic or the Antarctic doesn't seem like a place when we can find a lot of forest, but it's not entirely true. We have only have tundra, but also taiga, where we have lots of forests and lots of lots of pines, and this is the scenery that the aurora borealis can occur as well. So why did people think that it has something to do with pine cones or pine needles? So that was one of the leading theories. So during this geomagnetic storms, the atmosphere can hold very abnormal, very high electric field, very intense electric field. So there is a different, so because of this gradient of static electric field between the air and between some objects on the earth. And everything that is spiky, like needles, like pine cones, would be like a perfect surface to unload this electricity, right? Like to make this little electric shock from like when we sometimes experience it, like we're touching a doorknob or something like this, and there is this little shock from the doorknob to our hand, to our finger. It can, then we can always almost hear it like it's a cracking sound. So that's what people heard, like a cracking sound or clapping, or they described it like mostly cracking or clapping. Quite hard to describe. You'd have to just hear it. But the thing is that those electrical shocks, that this gradient happens much more higher in the atmosphere than on the tops of trees, even the highest trees. Okay, the highest trees can be 70 meters long, maybe not 70 meters, but quite tall. But still, it's not the place or the surface where the most of the this gradient electric shocks take place. So first of all, this Finnish scientist discovered that sometimes you can hear the aurora before even seeing it, because he was comparing geomagnetic activity with actual visual of the aurora. So what's cracking? If it's not the pine cones, it's not really cracking. What gives us audio impression of cracking? Again, it's depending on geomagnetic storm activity. These are the changes of geomagnetic field that cause those auroral sounds. They even have this official name, AS, auroral sounds. So these are not. This is not a contact of geomagnetic field with any kind of object on Earth. Just the cracking happens in the atmosphere itself. It seems like it's the inversion layer that cracks itself, and you can see here. Hopefully, you can see it. Let me. There's a gradient of static electric field. At the ground, it decreases, and it increases higher up, and the sound reflections can be heard here on the surface. So what we hear is not something creepy. It's just a geomagnetic field in the atmosphere. Okay, let's go to another riddle. So another riddle, or rather a question that sometimes heats the internet up, the discussion about climate change, whether it's real or not, whether it's human-induced or not. Sometimes one of the arguments is, well, but what about the Antarctic? If the Antarctic doesn't melt, it simply means that there is no climate change, no climate warming, which is of course not true. And the answer to this question, does the Antarctic contradict the climate warming, the climate change? Is no, it does not contradict. In fact, it can be explained, and also it changes over time. So we all know that the Arctic and Antarctic are two coldest regions on Earth, sitting on opposite poles, and they're not really like mirror images of each other, even though they're both very, very cold. Actually, we know that one of them is actually colder, because their environments are shaped differently and by very different forces, and this is why global warming is affecting them in a very different way. Actually, the coldest temperature ever recorded on Earth was, as you might know, not in the Arctic, but in the Antarctic, which was, it was colder than minus 93 Celsius degrees, which seems like impossible. And it was registered on the Russian, I think it was, no, it was still Soviet station Vostok back then. So the coldest temperature in the Arctic was actually more than 23 Celsius degrees warmer than the Antarctic record. Actually, the Arctic record was in Greenland in December 1991. So far, that of course what we recorded with our instruments. It was quite chilly. It was almost minus 70 Celsius degrees, but still far from minus 93, right? So why are those two regions formed differently and reacting differently? First of all, the Arctic Ocean keeps the atmosphere warmer. So water warms and cools more slowly than land. So the ocean and areas near the ocean have fewer extremes of temperature. This is why we haven't recorded minus 90 in the Arctic. So even when it's covered by ice, the relatively warm temperature of the Arctic Ocean has a very moderating effect on the climate in this region. So it helps the Arctic to keep slightly warmer than Antarctica, which doesn't mean warm, of course. But in the Antarctic, of course, the ocean also has a moderating effect on the climate, but near the coast. There is a peninsula, the Antarctic Peninsula, often called Banana Belt, due to its relatively warm temperature. Well, it's not hot, but still relatively warm. So coastal areas of Antarctica are known for some moss forests, because there are comparatively warm, comparatively high temperatures. So Antarctica has a definitely larger, is covered by the largest ice sheet on Earth. So the bright white surface of the ice sheet reflects most of the solar radiation and heat that reaches back to space. So the ice also cools the air directly above it, helping to keep Antarctica cool. Also, we don't often notice that the Antarctic is the highest continent on the planet, highest. in terms of its altitude. So due to thick layers of ice that raise its average elevation to around 3,000 meters. Of course, we have on other continents, we have very high mountains, but this is the average elevation, 3,000 meters. And so that, as we know, the temperature drops by about 1 Celsius degrees for every 100 meters of altitude you gain. So this high altitude also has a big impact on its temperature. So which is again different than the Arctic. Also, Antarctic is the windiest, not only the highest, but also the windiest continent on the planet. And this is very, very tough for our research teams that live there on our research stations, not only Polish research station, of course, with winds reaching even up to 300 kilometers per hour. So this is 3 times stronger than some of the hurricane force in the Beaufort scale. So these windy conditions mean that, of course, there's colder temperature, and also it feels even colder due to the chill. But, however, even though that Arctic is responding much more quickly and much more obviously than the Antarctic sea ice, now we are referring to sea ice, not the ice sheet, not the continent, not the ice sheet. So the Antarctic stayed relatively stable, and also Antarctic sea ice stayed relatively stable, at least according to the long-term studies monitoring the state and the patterns in the Antarctic region. So how does sea ice behave in face of climate change in both those regions? So in the Arctic climate, change is particularly noticeable, change in the sea ice. Decline in sea ice, and we have decades of observations and models to prove that the Antarctica, the changes lead primarily to melting of ice shelves and accelerating of calving of icebergs. But actually it is expected that due to climate changes, those 2 regions will become more similar than previously. As you can see here, that it is expected that the Arctic sea ice will follow, or we might say, mimic the seasonal behavior of the Antarctic sea ice. Which means that in the Arctic, it will probably form in the winter and almost completely vanish in the summer. So about those theories that climate change doesn't really exist because the Antarctic, no. Is climate change visible in our southern polar region as well? So in 2014, the record high sea ice in Antarctica was observed. So we might say, oh, there is a record high in the sea ice, so it's not a problem. It seems that the Antarctic is not reacting to the climate change, but it is far from the truth. First of all, the differences were not so big. The record was a tiny higher than the average. But actually, that was 2014. Now we're 2023, and it's actually really different in Antarctica. And it's actually a very sudden change. And as you can observe here, we have a very sudden and very rapid record low. So it seems that the sea ice extent, here measured in millions of square kilometers, is also starting to decline quite rapidly in the southern region. Like it seems like the cooling effect that all the structure and how the southern polar region is built and formed is not working anymore. We might say. Still, this riddle is not completely solved and will not probably solved for a long time to 100%. And this is fresh research fresh from July 2023. This new research suggests that the vital layer of cold water on the seabed in the Antarctic, which circulates the globe and actually influences the ocean's ability to continue absorbing much of the heat, much of the rise in atmospheric heat and greenhouse gas emissions, it actually heating up itself and it's shrinking. So like its capacity to moderate the climate warming effect is done or almost done. So much of this is a result of human-made climate change, which is melting Antarctic ice shelves and disrupting this complex system that controls the circulations. But also it seems that as far as the part of 30 years, last 30 years are concerned, actually also a natural cycle might add up to it and can be partly responsible for the changes observed, at least according to this study from July 2023. So it actually can be linked to some natural climate cycle along with our activity disrupting deep water circulations, ocean currents, and so on. And the very last riddle, maybe not such a gloomy one, just like the one before related to climate change, and it seems that unfortunately, we are losing, on one hand, due to our activities, and on the other hand, due to some natural cycles, we're losing like those safety spaces, safety areas that helped us, unknowingly to us, or knowingly, but without our effort, to moderate some of the heating effect, but also those areas, even as big, as potent as Antarctic, they do not have an unlimited capacity to absorb the heat and absorb greenhouse gases, and this is very worrying. So let's end on a more positive note, or a neutral note maybe. Is it actually warm in an igloo? Why do people, for example, Inuit people, basically that's their invention. Why do Inuit people build houses made of actually snow, not ice? But that's I think it's quite clear that it's not that igloo is built of ice blocks, actually built of very packed snow blocks. Well, first of all, they didn't have a choice. So with no wood in the area, with or little wood maybe, rather no wood. They had no other building material, and they were still in need of shelter. So people started first hiding in caves, right? So with no caves, no wood, they had no other way to shelter themselves from very harsh weather conditions. But is it actually effective? And also, why is it effective? We can observe how smart the whole construction of the igloo is, using people's body heat, people's breath as a heating system. So first we have an insulation. The insulation is provided by very densely packed snow, like I said, snow and ice maybe. those snow and ice blocks, but like I said, it's not like they're cut out of ice. They're solidified snow and ice. So this insulation stops body's natural heat, bodies meaning people living in the or sleeping in the igloo. It insulates the heat from escaping right out into the atmosphere, so it keeps it inside the igloo itself. So on the outside, the temperature may be even minus 45 Celsius degrees, but on the inside, the temperature may range from +7 to +16 Celsius degrees, which is of course not hot and not something that we would be accustomed to in Europe, but still with very warm clothes. That's at least allows to survive without hypothermia. It might be surprising that an igloo is built as a spiral, actually. So the first cycle of those blocks is placed tilting slightly like inward, and once the layer is complete, there is a slope cut into the top of the block. So the remaining layers form sort of a spiral shape. So if you try to peel an orange in one go without removing your knife, that's how it would be built. Those following layers of igloo going up and up to the top. So this spiral placement of snow ice blocks gives the igloo its strength. And eventually the sealing will form, leaving just a small gap at the top of the spiral, and it's a ventilation hole that is, well, it needs the ventilation, so it needs a hole still. And another one is light opening, so at least when there is some natural light, it can be let in through this light opening. Actually, what I'm worried about is those trees behind the igloo. There are definitely no trees in the areas where most igloos are built, but you know, maybe it's a trend to try and build an igloo by yourself. So what you not necessarily being in Greenland, for example. And the sleeping area is quite elevated. This entrance and storage of food, for example, is a little bit lower. The question is, if it's built of packed snow with ice, why doesn't it melt with 16 degrees? Plus 16 Celsius degrees on the inside, people breathing, people giving away their body heat. And also you can do a fire and inside the igloo, one does it melt? Well, actually it does melt a little bit, but then it refreezes. And actually, it also helps to keep the structure of the igloo together. So it melts a little bit. It doesn't melt to drip, it refreezes. And because there was water sitting directly on the still frozen snow of igloo. So it creates an extra layer on those slows, so this crust of ice that helps to strengthen the walls and prevents collapsing of the igloo. And snow deeper in the walls, not the inner side, stays frozen. Because it loses heat to the outside, and the outside, like I said, it can be minus 45 degrees, even in the areas where people, Inuits actually live. And this is a little bit of explanation of three phenomena, maybe four phenomenon, 3 modes of heat transfer that allow all this to happen. So let's start with insulation. Insulation, the snow, why is the snow used? Because first of all, it's available, but it's used because the air pockets trapped in it make it a very good insulator, because air is a great insulator. So it traps in heat by stopping the flow of air molecules. And this trapped air creates a barrier that slows down the transfer of heat and which helps to keep the heat inside a home or an igloo in the winter inside, and actually out in the summer, but we're here focusing on very cold climates rather. So the insulation, this barrier is called also called a thermal boundary. It's like a dividing line between the indoors and the outdoors. So we have insulation that allows Inuits to live in the igloo, and we have conduction, convection, and radiation. Here explained on a very simple image, heating up water using fire. So conduction involves molecules transferring their energy, their kinetic energy actually, to one another through the collisions of molecules. So this is conduction. There is convection, which occurs when hot air rises and allowing cooler air to come in and be heated. And the third phenomenon is radiation, or thermal radiation more accurately. It happens when those very fast accelerated charged particles release their electromagnetic radiations, which can be felt as heat. So as for convection, let's get back to this image. Why is sleeping area elevated in the igloo? Simply because of the phenomenon of convection, because the warmer area tends to go up, like I said. So here in the lower area serves as storage for food, for meat, and mostly, and the elevated sleeping area concentrates the heat here. Thank you very much. I hope I helped to solve some of the riddles, and most importantly, I tried to explain the why behind those riddles. So, like I said, not everything is explained, which does not mean that science cannot explain everything. It will probably at some point. As you can see, some of those studies were very recent, even as recent as July 2023. So unlike Lord Kelvin said in 1900, we do have much to discover. We do not understand everything yet, which is good because there's still area for new discoveries and new research to be conducted. Thank you.